Alright, so this is an explanation of the answer to the previous lab, the one that was assigned on Thursday. So I'm going to go through these one by one and explain the answers. Question number 1. The LD load instruction loads content from RAM to a register. The RAM location is specified by another register. The general format is like this, where X is a register A, B, C, or D, and Y is also a register A, B, C, or D. Note that X and Y can be the same register. And the question is asking you to look up the opcode table, find out the actual binary opcode of LDCD. So C goes to the placeholder of X, D goes to the placeholder of Y. So when we locate the opcode table, we first locate the LD instruction, which is where I'm already at. So you can see that XX are bit 2 and 3, and then YY are bit 0 and 1. And then the fixed bits are 0, 1, 1, 1 as the most significant 4 bits. So this will be a 7. The 0, 1, 1, 1 is going to be a 7. And then okay, let me read the question again because I can't remember which one is which one. So C is X. The answer should have exactly 8 bits, which implies it is a base 2 answer. So that means 0, 1, 1, 1 is the 7, the fixed part, and then C is represented by 1, 0, and then D is represented by 1, 1. So that should be the answer of question number 1. It is basically hand assembling the instructions instead of using the assembler to do it. Now, for those of you who go like, but I don't want to do this by hand. Well, you could use the assembler. So when you switch to the assembler, go to the source tab and just enter that instruction, which is LDCD. And then you go to the assemble tab is great for a lot of things, including figuring out what the opcode is. Now, but it only gives you a 7B, which means you have to translate the 7B back into binary, which is 0, 1, 1, 1, 1, 0, 1, 1. So yeah, so this solution saves you the time of you don't have to figure out the bit pattern, but you still have to translate the hexadecimal digits back into base 2 digits. So whether it's worth doing or not is up to you. So now we move on to the next question. Question number 2. Now start up Logisim and load processor 0003.circ in the ROM component. What is the address of the first microcode slice to implement this instruction? Alright, so once again, there are many ways to do this. You can do this theoretically. You can also do this empirically. Let me first start up Logisim first. Okay. Well, apparently it's running already, so let me just find it. There we go. Alright, so we now have Logisim up and running. So there are 2 ways to answer this question. The first way to answer it is to theoretically figure out, how things connect. Because we know the instruction register eventually gets loaded into the microcode pointer, which then points to the correct location in ROM during the decode cycle. Now, we did talk about the decode cycle, so if you have a question about what the decode cycle is, you might want to either review the notes or watch the video again. Because the instruction is 7B, so that means 7B eventually will get loaded into the instruction register using the fetch cycle. And once again, we talked about the fetch cycle, so if you don't remember what the fetch cycle is, it is time to review the video. That eventually gets loaded into the microcode pointer, but when things are loaded into the microcode pointer, it is left shifted by 4 bits because of the way the splitter is structured. That means the microcode pointer is going to have 7B0 in it. As a result, in the ROM, you have to go to location 7B0 to locate. So the address is going to be 7B0. So you have to you have to read the question carefully to find out what it is asking. State what is the address. So in this case, we just want to know the address, and we want the answer in hexadecimal digits without the 0x prefix. So that would just be 7B0 here. Moving on to question number 3. LD is a simple instruction. It is implemented by a single slice of microcode. A single slice means it is a single location in the ROM. In microcode, look up the ROM of the processor and find out what is the first slice of the microcode of the LDCD instruction. State your answer in hexadecimal, all lowercase, and without the 0x prefix. So that means we just go here, right click, go to edit content, because otherwise you can't really locate that easily. Then we go to 7B0, and this is the correct answer. I'm not sure whether it will let you copy and paste, so I'm going to give it a try. Yep, it does. Cool. Question number 4. The ST instruction has the mnemonic syntax of ST in parentheses Y, comma X. In this case, the value of register X is copied to the RAM location pointed to by register Y. Again, X is one of the 4 registers, A, B, C, or D, and Y can be the same one of the same 4 registers. How many variants are there to this particular ST instruction? Well, because Y has 4 choices, and that does not impact my choices for X, so now we have 4 times 4, so the answer is 16. Question number 5. The assembler accepts label definition. This is a handy feature because otherwise the programmer will need to count the number of bytes used in code. A label definition is an identifier, same rules as a C variable name, followed immediately by a colon. A label definition must be the first thing of a line, and there should be nothing other than comments starting with / after a label definition. For example, the following line defines the label L1. So this part here is really just an example of what the syntax looks like. L1 has nothing to do with this question other than serving as an example. Note that a label is a symbolic name of the address of the next byte. So this really is the key of what a label is it is the symbolic name of the address of the next byte in the program. In other words, in the following code, L2 is the symbolic name of the address of the first byte of the LDI instruction. There's only one LDI instruction, so it's pretty clear which one we are talking about. Assuming the above code is at the beginning of a program, what is the value represented by the label L2? Alright, so the first thing is we already know L2 is the symbolic name of the address of the LDI instruction. So the question is really asking what is the address of the LDI instruction? That's basically what the question is asking. To answer this question, there are 2 ways to do it, and since I haven't really talked about how to count bytes manually, so that leaves only one way to do this, in a fair way. So what you do is you copy and paste this code into the source tab of the assembler, and then you switch to the assemble tab. Now we did talk about the assemble tab in the previous lab, and we did talk about how column W, if you just kind of hover over a column, it actually self-documents, but column W is the address in hexadecimal. And over here, we can see that 01 is the address of the first byte of the LDI instruction. And that's the answer. It really is just 1. Question number 6. Labels can be used as an immediate value. This means the LDI instruction can use a label as the I part. This is quite handy because very often we need to get content from a specific location in memory, and symbols make this easy. Observe the following code. When the program gets to the halt instruction, what is the value of the register B? Specify the answer as an 8-bit binary number. So this is an interesting question because there are, once again, multiple ways to answer this question. So I'm going to start with the theoretical way to answer this question, and then I will proceed with the empirical way to answer this question. The theoretical way to answer this question is going to involve copying and pasting this into the assembler first. So once again, we go to the source tab and just paste the new code in, and then we go to the assemble tab. The assemble tab shows you the actual bytes of the entire program. So we still have to kind of understand what these instructions mean. LDIA L1 is loading the value of the label into register A. Now, how do we know that? Because the opcode table tells us what LDI does. This is the LDI instruction, LDI XI, and the C notation tells you there are several ways to interpret this. In terms of the raw mechanism, this is the actual raw mechanism. We are copying whatever the program counter points to register X, and then we auto increment the program counter. That's the actual mechanism. However, the other way to look at this is to look at column D. All it does is to load the constant value I, right after the opcode into the register. So knowing that, and we switch back to the assembler. So basically what A ends up as is the value of L1. So now we just need to know what is the value of L1. In this case, L1 is the address of the ST instruction, and according to column W, the ST instruction has an address of 04. So the first instruction ends up loading A with a constant of 4. The second instruction is an LD instruction. So once again, we go to the opcode table to figure out what the LD instruction is going to do. The LD instruction, which is here, is just going to copy whatever the second register is pointing to in RAM and copy the content at that location to register X, which is the first register. So in this case, we're going to the location that register A is pointing to. Because A has a value of 4, we go to location 4, which is here. And then we copy the content, which is FC, into register B. So register B ends up with a value of FC. And that's the answer. Now we go back to the question to see what it is expecting. The answer should be an 8-bit binary number. So FC is 1111 for the F, and then C is 1100. So that would be the answer of question number 6. But this is the theoretical way to answer the question. The empirical way to answer the question is simply to run the program, because we know the halt instruction. Nothing can get past the processor cannot execute past the halt instruction, so we can just run the code. So to run the code, we go to the RAM file, we go to File, and then we download the CSV, and we save the file as a particular name, and I'll call this Q6. This is for question number 6. There we go. And then we switch to LogicSim, and then we reset simulation. Then we go to RAM, right click, load image, and then specify the file that we were just talking about, which is in the temp folder, and I believe it's called q6.csv. The program is now in, and we want to run this as quickly as possible, so we make sure that my tick frequency is maximized, and then we turn on ticking, and by the time the halt pin becomes a 1, which is actually pretty quickly, we can stop the ticks, and then we go to register B. So the content of register B is actually reflected on the outside already. So this is register B, and it is 1111 1100, just like how we figure it out, without using the simulator to help us. Question number 7. So question number 7 basically talks about what the byte thing is, and so a good portion of this question is really instruction to tell you what a byte instruction, not its instruction, but a byte directive is. It really just a way so that we can specify the content of a byte in memory. And when you have consecutive byte directives, you basically are defining consecutive. You're basically specifying the content of consecutive bytes in RAM. The actual question is this part here. It says you can also write an entire program using the byte directive because you can figure out the binary opcode yourself. The following is such a program. When this program cannot go any further, implying that it gets to the halt instruction, what is the value in register B? So it's kind of the same deal, right? We just have to run the code, and by the time we get to the halt instruction, we examine register B, and that would be the end of it. So once again, there are two ways to answer this question. You can try to answer this question theoretically, or you can try to answer this question empirically. So this time I think I'm going to do the theoretical way first. So the theoretical way to do this is to look at each one of these actual numerical value and figure out what opcode they're corresponding to. In other words, we're doing exactly the reverse of what the assembler normally do. We start with a bit pattern, and then we reverse it back to the actual instruction behind that binary opcode. So we'll start with 1. This is 109, and the first thing we need to do is to convert it into base 2. I don't have my tablet up and running, and I'm too lazy to get it up and running, so I'm going to use mouse pad because this is just a simple base conversion thing. And mouse pad should have opened it somewhere. Where is my mouse pad? There we go. Alright, so we look at 109 in base 10 and we try to convert it into base 2. So we know there's a 64, there is a 32 that accounts for 96. 109 minus 96 is less than 16, so we don't have a 16, but there's an 8 in it. So now we have 104. So we still have a 5, so a 5 has a 4 and a 1. Alright, so now we look at this in base 10, and then we just enter the bits, right? So there's 0, 128, 164, 132, 0 of 16, 18, 14, no 2, and 11. So now we can see the bit pattern is 0, 110, 1101 in base 2. Then what we do is we take this bit pattern and then we go back to the opcode table to match. And this time the match is exactly the opposite. Okay, so we don't even look at the other columns. We look at column A, and then we see, okay, which one of these rows. Sometimes there are multiple ones, not for this homework assignment, but sometimes there are multiple rows that can match. And in this case, 0, 1, 1, 0. Okay, so row 21 and row 22 are potentially matching, but we can see how one of them has these two 1s. That would be row 22. So row 21 does not match, and only row 22 is matching. So row 22 considers the 0, 1 as XX, which specifies a register. So we have our LDI instruction back. So this is LDI, and the register being used is specified by 0, 1, so that specifies the B register. And the constant or the immediate value is not specified by the opcode itself. It is the byte right after the opcode. So now we go back to the question. So the next byte is simply the value of L1. So that means, this is really just LDI L1. Alright, moving on to the next instruction. The next instruction is specified by the decimal value of 117. So we're going to do the same base conversion here. 117 is 64 plus 32. That accounts for 96. This time we do have a 16. So with all three, I think we are up to 112. So that we have 5 left, and that's why we don't have an 8. We do have a 4 and a 1. So now when we convert this into binary, we have 0, 128, 164, 132, 116, 08, 14, 02, and 11. So I think that is correct. We can always reverse the whole process and, verify the answer. So we'll go ahead and reverse the process and see whether we get the same value back. We'll see whether we get 117 back. So to reverse the process, I will look at 64 and 16 first. Those two added would be an 80. And then we have 32, so we have 112. 112 plus 4 is 116. 116 plus 1 is 117. So I think we got it. Okay. All right. So now we have 0111, 0101 as a binary bit pattern specified by 117. And now we need to look up the opcode table to reverse the process. So we can see there's only one row that starts with 0111. And it specifies XXYY as the least significant 4 bits. So that means this one is LD, and then both X and Y are specifying the same register, which is B and B. So this is my next instruction. Going back to the question. The next byte is a byte of 1. That is just the halt instruction. And then at L1, we have byte L1. In other words, whatever is at this location has the same value as L1 itself. So now what we can do is we can actually do some counting. This is location 0, location 1, location 2, location 3. So byte L1 itself is at location 4, which means L1 as a label has a value of 4. So that means this byte here is basically the same thing as a byte 4 because label L1 is 4. It's the symbolic name of 4. So that means, so when we run this code without using the simulator, we just run this code and go like, okay, this instruction is going to copy 4 into register B. This instruction is going to go to location 4 in RAM, grab its content at location 4, and then put that content into register B. But we know at location 4 it simply has a value of 4, so B should end up with a value of 4. So that's one way to do it. This is kind of the hard way to do it, but I think it's doable, given what we have talked about up to this point. But the other way to do this is a whole lot simpler. I will now illustrate the other way to do it. We simply do a copy, go to the assembler, go to source, and paste. There we go. We go to RAM file, and go to file, download, specify CSV, and save the file as I think this is Q8. Then we switch back to the processor, in LogiSim. Reset the processor first. So go to simulate and then reset simulation. Go to the RAM component, right click, load image. and this time we want to specify q8.csv, and then press open. So now we got the program loaded. And this time I'm going to do it a little bit smarter. I scroll down so that I can see the hold pin before I start simulation, start ticking. There we go. The program almost concludes, like immediately, because these are very quick and small instructions and there are no loops in this particular program. So now I can stop the ticking. And then we just have to go back to look at register B. And register B is specifying a value of 4 because we have 0, 0, 0, 0, 0, 1, 0, 0. So when you count, what this 1 is representing, this 0 is telling us that we have none of 1, none of 2, 1 of 4, and none of all of the other ones. So register B has a value of 4. What is left for us to pay attention is what is the question asking. Is it asking for an answer in base 10, which is 4, or is it asking for the answer in base 2, which is 100? And it's quite specific that we're being asked to enter a base 10 integer, so that's just 4. And I think that's it. So I'm gonna submit the quiz. And I got 7 out of 7 points. So I think I made a mistake, somewhere within this question. One of these questions is worth 0 points because I made a mistake and made it a 0. But when we go through all of these questions, they are all. Oh, okay, there are only 7 questions. My mistake, I thought there were 8 questions. Okay, there were only 7 questions. So that's kind of a quick explanation of this lab. So the next thing I want you guys to do over the weekend, yes, you're supposed to be studying as well. For each hour in lecture, not counting the lab, for each hour in lecture, you're supposed to spend 2 extra hours to study, do the homework. Since we don't have any homework other than the lab most of the time, so that means even more studying and then preparing for the next class. So you do have, you're supposed to spend 160 minutes for each 80-minute lecture to do all of these extra things. So what I want you to do, with your 160 minutes is to go through the simulator so that you can find out exactly mechanically in the processor what it is actually doing with the LD instruction, with the ST instruction, and with the LDI instruction. Use the same technique that I used on Thursday and apply that to run one of these test programs here. If you want to know which program you should be using, I would say the one in question number 5 is a good one to look at, and also the one in question number 6 is also a good one to look at as well. So that's sort of what I expect people to do to quote unquote study for this class. Now, if some people decide, but I don't want to do this, that's actually okay with me. However, I can already tell most people that if you don't study in this particular way, the rest of the semester is gonna be very, very hard. Because this class is each session is built upon is building upon the material that we have already introduced. You can kind of see how I used base conversion in this particular lab, how I made use of the opcode table in this lab, how I made use of the assemble tab in the assembler in this particular lab, and all of those were material that we have already introduced in previous labs and classes. So that's why I think it is super important to go to the simulator and basically, okay, let me illustrate what I mean by that. I'm not going to do the entire thing, but I will do a portion of that. All right, so I'm gonna reset the processor without resetting RAM, because I don't want to have to reload the RAM with the content. And you can see how pressing the reset button does not actually change the content of RAM. But you need to make sure the clock is at 0 before you hit that reset button. That's kind of the caveat. Okay, I haven't been able to find a solution where you're clicking that reset button can also reset the clock state from a 1 back to a 0. So anyway, now we're at the beginning of this instruction again. So what I want you to do is to use Control T. Okay, if you look at Control T, it is a single edge. Okay, so I want you to use Control T to single edge through the execution of this program. When it executes, when it gets to the execute cycle of the instructions, I want you to examine every single component in the processor to find out which one is active, which one is going to be updated, and how it is going to be updated by looking at the multiplexers and the demultiplexers, and so on. I know it is tedious because that's what we did on Thursday, but the more you do this, the less tedious and the less time consuming it will become over time. Then you will have mastery over the instruction set as well as the architecture of the processor, which makes the topics for the rest of the semester a whole lot easier to deal with. Not doing this means it is not likely that that person will understand the architecture thoroughly enough to get a good score in the second exam. And then because all of the further material is built upon a thorough understanding of the architecture, what each instruction is actually doing and how it's doing it, that means the rest of the semester is going to be very, very difficult for those people. So as such, I am just recommending people to do this. And if you cannot figure out something, you can go ahead and ask me. Okay, you can ask in class, you can also ask outside of class time. But the point is, I really want everybody to thoroughly understand how every single opcode work in terms of the configuration of the components inside the processor, which component is active, and how the multiplexers and demultiplexers act as routers to route data from one component to another component. All right, so you have been recommended, okay, because that's all I can do. Okay, I cannot control study habits of other people. I cannot control how other people study the material. I cannot control whether people allocate time to study or not. That is way beyond my control. But what is within my control is to make this recommendation. All right, so I think I am done with nagging in dad mode. So I'm gonna shut up now and upload this video and send the link to you. All right, have a nice weekend. I will see you guys on Tuesday.